This example will be for a statically determinate beam with an overhang here, or a cantilever. There's 2 force per lengths applied to the cantilever. The central span is 10 units of length. The overhang is 5 units of length. We can do this problem exactly and get the bending moment diagram exactly without any statics. This is probably historic. How do we do this? So here's the beam recreated. There's the 10, let's call it feet, 10-foot span, and then the 5-foot overhang. What we need to do is establish the moment at a few points, really 3 points. And we know that the moment is free, 0 at the free end here, so that one is given. So I'm going to establish some moment here and some moment here. And what I'm going to do is combine the restraining moment with the free moment. So the idea here is that there's a free moment, which would be WL squared over 8 if we were to do this algebraically, and then W times overhang over 2. And we would combine these two as we do in the product integrals, but there's no algebra here. It's just this, it's the superposition of this and this. The only trick is that this WL squared over 8 is not horizontal. It's slanted because it begins at the restraining moment. So how do we get the moments? Well, we use the Muller-Breslau method here. We crack the beam and insert a unit rotation. We get the loft at the point where the load is the centroid of the load. So here that would be a 2.5-foot span, so that the loft is 1.25. You could do this on a napkin. And the moment at that point is this number. I have to multiply it by a scale. So I scaled the moment diagram up. So there's my first moment halfway along the cantilever. I apply the Muller-Breslau method for the second crack here. You could do this on a napkin again. There's the second. And then I fit a polynomial. That's all I did. I did this on the computer, but you could certainly just sketch this out. It's just a curve. But these 2 points are exact, and the third point, of course, the 0 point is exact. Then I'm going to get the WL squared over 8. And as I said, that's the only tricky part, is that you have to have that on the incline here. So I find the midpoint of that incline here. And then this circle is the WL squared over 8 if this was algebraic, but I'm not doing it algebraically. I'm doing it Muller-Breslau. So I crack it at the midspan. I find the loft at the midspan of each of those. And again, this is super simple, like napkin sketch stuff. And I get that point. That's the WL squared over 8 if you were doing this algebraically. And now look how cool this loft is. It's like a hanging chain that goes from here to here. And what I can do then is just find the worst moment, which is not here, it's over here, right there, and I just wiggle this around until I find it, boom, and it's 14.06, which is exactly correct. That is, if you were to do this algebraically, there's the 14.06. So it's kind of incredible. I don't think this has ever been done before. To get the moments has been done before using Muller-Breslau, but to get the bending moment diagram from this, I think that that's unique.